Okay, quantum theory. Chemical behavior of an element is determined by the number and arrangement of its electrons. We know that by looking at the quantum numbers. Quantum numbers help us understand the arrangement of electrons in an atom. And remember, outer shell electrons do the reacting, but we have to look at all of the electrons to see how many energy levels there are in an atom, because that also will affect reactivity. The principal quantum number is N. N corresponds to the energy level. So energy level 1, 2, 3, or 4. The greatest number of electrons possible in any one energy level is 2n squared. So if we had principal quantum number 1, or energy level 1, we'd put the 1 where the n is sitting. 1 times 1 is 1 times 2 is 2. If we had principal quantum number 2, or the second energy level, we'd take the 2 and put it where the n is sitting. 2 times 2 is 4, 4 times 2 is 8. If we were talking the principal quantum number 3, we'd be taking 3 times 3 is 9, times 2 is 18. Principal quantum number is N, and it corresponds to the energy level. Energy levels are made up of many sublevels. So there's sublevels within each energy level. So it's like broken down into smaller categories. The second quantum number, L, describes the sublevels within an energy level. The first sublevel is S. It contains 1 pair of electrons. The second sublevel is P, contains 3 pair of electrons. The third sublevel is D, contains 5 pair of electrons. The fourth sublevel is 5 and contains 7 pairs of electrons. Valence electrons is a fancy name for saying outer shell electrons, which are the important ones. The space occupied by 1 pair of electrons is the orbital, and it's found anywhere within that orbital. The probability of finding it anywhere within that orbital would be where we find it. Orbitals are described by using the third quantum number m. Orbitals that are alike in size, shape, and energy, but the direction the electrons are moving, are known as being degenerate. Okay, electron configurations. We need to know the electron arrangement of an atom in order to predict the atom's reactivity. We know that electron arrangement by doing an electron configuration. To do an electron configuration, you're going to need your arrow diagram. And you start with the far left arrow where it says 1s. And I told you on the last page, S's can hold 2 electrons. P's can hold 6 electrons. D's can hold 10, and F's can hold 14 electrons. And you have to remember that as you're following through this. So you would start at 1s, 2, 2s2, 2p6, 3s2, 4p6, 3p6, 4s2. You just follow the arrow diagram. These superscript numbers are referring to electrons. I'm going to show you some examples of these. This may be kind of confusing right now, but I'm going to show you some examples. But when you're doing electron configurations, you need to follow the arrow diagram listing the orbitals. And if you do that, you'll be okay. In studying atoms, a primary concern will be electrons in the outermost energy level. These electrons most often are involved in the chemical reactions. It is useful to draw these outer electrons around the symbol known as a Lewis dot diagram, and we'll be doing that later on. I want to show you some tables before I show you some information about electron configurations. This table, you also picked up a handout that's very similar to this, showing you the principal quantum number n, so you're at energy level 1, 2, 3, or 4, the number of sublevels that are found at each energy level. So energy level 1 only has S. Energy level 2 will have S and P. Once you get to energy level 3, it will hold the S sublevel, the P sublevel, and the D sublevel. And energy level 4 can hold the S, P, Ds, and Fs. This shows you the number of orbitals. The S has 1 orbital. If you put S and P together, that's a total of 4, because S is 1 and P's are 3. Then you get S, P's, and D's. There's 9 orbitals. S, P, D's, and F's, there's 16 orbitals. Each orbital can hold 2 electrons. Electrons pair up in twos. They like to be in twos. They're just like a couple. So it makes sense that if we had S, P, D, and F, S is 1 orbital, P is 3 orbitals, D is 5 orbitals. Add that up, that's 9. 2 electrons in 9 orbitals, that's 18. And again, that's the maximum amount of electrons in a certain energy level. That's not total electrons at that point, it's just sitting at that level. I also gave you a chart of the sublevels, S, P, D, and F. S is the 1 orbital, P's 3, D's 5, F is 7. And again, electrons pair up. So if you're 1 orbital, you actually have 2 electrons. 3, there can be the most is 6. 5, 10, and 7, 14. And then this is just showing spin. They either spin kind of right or left. So lithium has 3 electrons. It fills up the 1s first, and then the third one goes to 2s. There's beryllium, then we have boron, and you can see in carbon, we fill up the s, we fill up the second s, and then each of these p's has to get 1 before it fills up, before they pair up. So look at nitrogen, 2 sitting in the 1s, 2 sitting in 2s, but each of the p sublevels gets an electron. They're not pairing up yet. They don't pair up until you'd have more. So if you look at neon, and then there's sodium. So what I may do, I may give you an element, and I'll give you, instead of squares, I usually do circles. You're going to have to draw arrows showing electrons. So you'd have something that looked like this, but instead of squares, they'd be circles. So you still have to know number of electrons. Remember, number of electrons is equal to the number of protons. Number of protons is the atomic number. Okay, let's go back. I'm going to do some examples for you. I'm just going to use this space around this chart here because I didn't input an empty slide. Okay, I'm going to draw. Okay, let's draw helium. Helium has 2 electrons. Energy level 1 contains the S sublevel. The S sublevel can hold 2 electrons right there. Here's the S sublevel, it can hold 2. Okay, let's go ahead and draw in oxygen. First S sublevel fills up, energy level 1 with its S sublevel. That is full, then we have to go to energy level 2. First it's going to fill is the S, and then an electron is going to go to each of the P's, and then it will pair up. So this right here is like 1s2, 2s2, and each of these is a P, 2p4. Then we'll have neon. It's going to fill up the first energy level, only holds the S sublevel, and then it can only have 2 electrons. So then we head to the second energy level. It's going to fill up the S sublevel, that can only hold 2. The P can hold up to 6. 1, 2, 3, 4, 5, 6. There's neon. Now for the next element, if you look at neon, the next element on the periodic table is sodium. And we are going to have to add in another energy level because neon, the second energy level, is full. The P's filled up. So I'm going to do sodium. 1s2, 2s2, 2p6, 3s1, if you're following along using your arrow diagram. Okay, so again, that's 1s2, 2s2, 2p6, 3s1. You will never have to draw diagrams like that. You will be doing electron configurations. To do electron configurations, you need to know the atomic number, because the atomic number is the number of protons, and the number of protons is equal to the number of electrons. Okay, we'll practice that in class. Now what I want to do, I'm going to give you an electron configuration. Okay, and from here, you're going to figure out how many electrons are in the outer shell and what element this is. To figure electrons in the outer shell, you look at the highest energy level that was written down. I have 1s, 2s, 3s, and I see some 4s here. Okay, so I look to see how many electrons are at the 4 energy level. I have 2 sitting here, and I have 3 sitting here. So I have a total of 5 electrons at the highest energy level. That's my outer shell electrons. The highest energy level you wrote down, you add up all the electrons at that energy level. That's your outer shell electrons. It will never be more than 8. To find the element, you look at the highest energy level written down. And then you look at the last sub-level you wrote down. And you need your periodic table. So on your periodic table, you're going to go to period 4 because that was the highest energy level that you wrote down. And you're going to go to the P part of the periodic table. I'm just going to tell you right now, families 1A and 2A represent S1, S2. Family 3A is P1, 4A is P2, 5A is P3, 6A is P4, 7A is P5, 8A is P6. If you get to the D's, you look at the transitionals. D can hold up to 10 electrons. If you look there, there's 10 families. The F's can hold up to 14 electrons. The F family corresponds to the lanthanoid and actinoid series at the bottom of the periodic table, and if you count that, there's 14 columns there, or rows. Columns, sorry, 14 columns. Okay, let's get back to the example. P3, so the highest energy level was 4, so I'm at the period 4. P3, so P1 was, so I start with family 3A, that's 1, and then I go over to 2 to 3. I am at 5A, which is arsenic. So I have arsenic, and it has 5 electrons in the outer shell. There's its dot diagram. Dot diagrams only show outer shell electrons. So we will be practicing that in class. I think that may be all that you need to know for this lecture. We're just going to be doing a lot of practicing in class. You're going to be practicing writing writing electron configurations. I'm going to give you an element. You have to find the number of electrons, write electron configurations. I may give you an electron configuration, you have to figure outer shell electrons. Once you figure outer shell electrons, then you need to figure out what element it is and do its dot diagram. Lots of practice tomorrow.